Okay, so we discussed earlier the concept of molar heat of molar enthalpy of formation, right? So this was represented by this. In that, while defining that, we came across this term of the constituting elements and the reference to the elemental reference states. So the molar enthalpy of formation is defined like this. The delta H of the reaction for the formation of 1 mole of a compound, that's the term molar, from its constituting elements, right? So for example, like if you want to find out the molar enthalpy of formation of SiO2, which is the quartz, we have to go to its constituting elements. What is the constituting elements of quartz? Silicon and oxygen. So in here, I have listed different types of equations, all which all of them produce silica, which is all of them produce quartz from silicon and oxygen. However, the constituting elements, which is the silicon and the oxygen, are in different states. How? You see in here, in the first equation, the silicon is in the crystalline state, and oxygen is in the gaseous state. For the second, and for that, we have the delta H of that reaction at 298 Kelvin is minus 910.7 kilojoule per mole. But if we take silica liquid instead of silica crystal, we get quartz, but the delta H changes for obvious reasons. Now, there is an energy exchange. You cannot go from silica crystal to silicon liquid without any energy exchange. Actually, the energy exchange when you want to go from silicon crystal to silicon liquid is 48.5 kilojoules. So it takes 48 kilojoules per mole of energy to change 48 kilojoules of energy is required to convert 1 mole of silica crystal into 1 mole of silica liquid. And that is why you have a different delta H of formation here. Now, again, if you have silicon gas, the delta H of the reaction has changed. Now, similar thing goes for oxygen too. Like you had oxygen gas in here, but in here you have oxygen atoms, like 2 moles of oxygen atoms. In here you get a different delta H and for the silicon crystal, and in here you have silicon gas with oxygen atoms, you get a different delta H. Now, all of them have formed silica, the quartz, all of them have formed quartz from its constituting elements, which being silicon and oxygen. But which one would you consider? Any one could be considered actually, like all of them are correct. None of them are wrong. All of them are correct. These are values that people have calculated by doing experiments. All of them are correct. But the problem with communicating science is you want something that people will follow, right? Like if you say that, if you ask anyone in the world, what is the molar enthalpy of formation of silica or quartz, all of them should come up with the same answer. To do that, what scientists did was they came up with the idea of elemental reference states. They said that all the constituting elements that you have must be in their elemental reference states. Now, what is an elemental reference state? Now, a reference state is generally the most stable state at that or at ambient temperature, which is 298. So this is the reference state. So now we have to find out of all these, out of silica crystal liquid and gas, silicon crystal liquid and gas, In order to find out the reference state of silicon, we have to find out what is the most stable state. Generally speaking, I'll come up with some of the reference states. There are some elements in which the reference state is not the most stable state, and I'll talk about them. But generally, we have to find out the most stable state. So what do you think is the most stable state of silicon at 298 Kelvin? Is it crystal, the solid, the liquid, or the gas? It is actually the crystal, right? Similarly, at an ambient condition, so you have two options, oxygen molecule, oxygen gas O2, or the oxygen, the atom. It's easy, right? Like at ambient conditions, the oxygen gas is the most stable state. So that becomes the reference state. So what is the reference state for silicon? It is a crystalline state. And what is the reference state for oxygen? It is the oxygen gas. Okay? So it became easier for the scientists to come up with the delta H. So this delta H became the delta H of formation, the molar enthalpy of formation of quartz. Okay, so this delta H became the molar enthalpy of formation of quartz. Why? Because we are creating quartz using the constituting elements which are themselves in their reference states. And what is that reference state? Generally, it is the most stable state at the ambient temperature. Now, extremely easy to understand is most of the gases that you see, right, like hydrogen, helium, neon, argon, krypton, xenon, radon, nitrogen, oxygen, fluorine, and chlorine. So these gases represent the reference state for these individual elements. So what is the elemental reference state for the element nitrogen? It is nitrogen gas. What is the elemental reference state for the element argon? It is the argon gas. Okay, so this is easy. Now, another concept that is there is, as I said, it is not always the most stable state that is there. What are the differences? Before understanding that, let me just tell by definition what is defined as the enthalpy of formation. So it's written here, I'm just reading out, that by definition, the enthalpy of formation of an element in its reference state is 0 at all temperatures. As I said before, that calculating the absolute value of H is not possible, right? The absolute value of enthalpy of anything is not possible. In order to solve this problem, we have to consider something as the baseline, as goes for physicists for calculating the potential. Like in order to find out the potential of anything on Earth, what they do is generally they take the potential on the surface of Earth as 0. And with that reference point, they calculate the potential of any other body, right? Similarly, what the chemists did is they said that, okay, now since we have this reference state, what we will say, well, we will assume the baseline will be that the enthalpy of formation of an element at its reference state will be taken as 0. So what that means is the delta H of formation of nitrogen gas of nitrogen gas will become 0 if that is in its elemental reference state. Okay, so this solves the problem of the baseline. So we have the baseline for everything. Now, I have not given the baseline for the solids. I'll just discuss it briefly, what that means and how we can calculate the baseline, the elemental reference state for solids. But for the gases, it's like that. So if anything, if any element is in its reference state, we will assume that the enthalpy of formation of that element is 0. Okay? I'm repeating once more that any element that is in its reference state, we will assume that the delta H of formation of that element, if it is in the reference state, is 0. Now we know what are the reference states of these gases. What about the solids? How do you calculate the reference states of the solids? Now let's, for example, you have silica, right? So silica melts at 1685 Kelvin. This is melting, and it boils at 3543 Kelvin. So for any, if we want to find out the elemental reference state of silicon, below this temperature, the elemental state will become silica solid. Okay? So now say, if I'm asking you, what is the elemental state of silicon at 500 Kelvin? The answer is solid, right? So below this temperature, the elemental state is solid. Between this to this temperature, the elemental state will be liquid silicon, and above this temperature, the reference state will become vaporized or gas silicons. Now this is the type of elemental reference state that is followed for a whole range of elements. Okay, now, this is the type which I'm just naming them because I don't have space to write that. So aluminium, bromine, gallium, iodine, lead, magnesium, mercury, platinum, potassium, silver, sodium, tin, zinc, all of these will have this kind of relationship, in which if we have that element below its melting point, the elemental reference state will be in the solid form. If the temperature in consideration is above the melting point but below the boiling point, the elemental reference state will be liquid. And if it is above the boiling point of that particular mineral, not of that particular element, not 1685 is not a fixed, 1685 is just for considering silica. All these elements that I said, aluminium, bromine, gallium, whatever, we will be considering their own melting temperatures and boiling temperatures, okay? To actually understand what is the elemental reference state for that element, okay? Now, there are some exceptions to this most stable thing. The notable exceptions are, there are 4 exceptions. The first is carbon, okay? The carbon's elemental state, that the reference state for carbon, I'm just noting down the exceptions here. For carbon, it is graphite. Now, carbon's most stable state at the ambient temperature may or may not be graphite, depending on the temperatures. But we generally take this as graphite. So I'll make another video, another part of this lecture in which I'll be discussing the different exceptions and how we understand these different exceptions, why were these exceptions made. But for now, just understand the elemental reference state for carbon is graphite. For phosphorus, there can be 2. Now, there is the confusion. You can have red phosphorus and you can have white phosphorus. So there will be some books who will be following red phosphorus as the reference state. So there will be some book who will be following white phosphorus. Now, we'll have to keep in mind while doing actual calculations that what is the elemental reference state that we are following for this. The third is sulfur, which is basically the orthorhombic and the monoclinic and the fourth is tin. SN, tin, which is found in the gray and the white. But generally, most of the books that you'll find is for the white, this is considered as the elemental reference state, although gray tin is basically the most stable state. But for most of the references that we'll be using, most of the books, they take white tin as the elemental reference state for tin. Okay. For sulfur, it's orthorhombic sulfur. Phosphorus can use both, and carbon is graphite. Okay. So this is there are certain other additional things in which you can we'll be discussing this in a little more detail, in which what if there are certain metals that can exist in different states even if it is in the solid state. So below melting point, silicon exists only in one state, right? There's no difference between the silicons at different temperatures. But for metals like there are many metals that I did not mention it here, the metals being iron. So iron can be stable at different, so below 143 Kelvin, iron exists in an alpha state. So the solid state of iron being alpha iron. Above that and below so between 1043 and 1185 Kelvin, iron exists in the beta form. So these are certain elemental reference states which people might need to understand. I'll be making a subsequent video regarding these. But for our purposes of this video, we should understand what is an elemental reference state and why elemental states are important. Why is it important to have a baseline from which you can measure the enthalpy changes, and what is the general rule of finding the reference state? It's generally the most stable state at the ambient temperatures. Okay.